This is Knowledge Engineering with Semantic Web Technologies. And this is the second extra part of the second lecture, RDF-based knowledge representations. And in this extra part of the lecture, we will talk in depth about SPARQL details. And today, we will focus on a little bit of SPARQL data management and on SPARQL semantics. SPARQL semantics, in the case here, I want to tell you a little bit about the algebra and an algebraic model which lies behind the interpretation of the query language SPARQL, because we want to know how SPARQL actually works. So, let's start first. We already know that with SPARQL we can query RDF databases. But on the other hand, SPARQL is really a fully flexed data manipulation language. This means you also have the possibility to update, to insert, and to delete RDF data. So first, we start here with inserting and deleting RDF data. So you see here two examples of SPARQL statements. The first one for a delete data and the second one for an insert data statement. And this is the most simplest form because with delete data, with this keyword, you can delete specific triples from a graph that you specify within your statement. And in the same way, with the insert data statement, you can insert specific triples into your graph that you specify here. So usually you start with a prefix definition, then with your option delete data or insert data, and then in curly braces, first you can refer to the graph that should be updated here, and then within curly braces again, you specify simply which RDF triples should be deleted or inserted. And here you simply follow the already known turtle language that we know. So on the first graph, you see that we want to delete a book with the title From the Earth to the Moon. And in the second one, we want to insert a book in our bookstore with the title Around the World in 80 Days. And we want to insert the triple that the book has the creator, DBpedia Jules Verne. So quite easy. But besides naming explicitly the triple you want to insert or to delete, of course, you can also specify triples and combine them with a graph pattern that filters or creates the underlying triples. So how does this work? This works quite similar, but here first we look at the delete statement. Here it's not delete data, it's simply delete. And here we also see a new keyword, the with keyword, and the with keyword specifies the default graph from which you want to delete or in which you want to insert. So with you specify the default graph. Nevertheless, you can also, or in addition, use the graph keyword to specify an additionally named graph within your statement. But then, of course, the graph statement overrides the previously defined with statement. Okay, so what is happening here? Here we try to delete RDF data based on bindings for a specific query pattern. And you see the query pattern here, so it means we say first with which graph, and this is a graph that holds addresses, and then I say I want to delete triples which should have the following form: person, property, and value. And here I only specify variables and not, as you might think, complete URI. So I use, of course, variables that can then be filled with the bindings of a query pattern that you find later on here in the where statement. So then in the where statement that follows, I try to explicitly specify the bindings for these patterns. And there I have again the three variables: person, property, and value. And of course here I say I want to delete all triples which have the fourth given name Harald. So quite easy. So you can here again combine more complex triple patterns in the where clause and can specify more complex delete or insert operations you want to achieve. So for example, in the delete statement, of course, you specify a triple here, only the period is left out, simply because Turtle allows abbreviation. If you only have one triple, you do not have necessarily to have a period in the end of the triple. So let's have a look at an insert statement that works in the same way. So what do we want to have here? So we are using the insert statement together again with RDF data based on bindings for a query pattern. So where is it useful? Not necessarily in the same graph, but for example, if you want to copy data from one graph to another graph and you want to specify only a specific part of the data that should be copied to the other graph. So then you can do it in the way you see it here. So we have an insert statement, so it's not insert data, it's only insert. So here I do not specify a default graph because I'm working in two graphs. So first I specify the graph in which we want to insert triples. So I name the graph that I want to insert triples to as bookstore, as you see here. And there I want to insert a triple which consists of the variables book, P, and O. And in the where pattern, I try to create the bindings for query patterns for these variables. So I specify a second graph, an alternative graph, in the where clause, where I refer to and where I take the triples from that I want to insert later on in my other graph, the graph that I have specified in the insert part. So let's have a look at the graph pattern here. So I say book, or the variable book, should have a property DC author, and then I have the author name, and I want to filter the names here with a regular expression simply with an author name Dickens. So I want to have all authors whose name contains the string Dickens, no matter whether it's in capital or lowercase letters. And then I want to extract all possible patterns or all possible triples that exist for that book. And these patterns then, consisting of the variables book, P, and O, will be inserted via the insert statement you see here. So it's quite simple. So you can do insert and delete via SPARQL. So it's a fully fledged data manipulation language. But keep in mind, this of course is only possible within a graph and on a SPARQL endpoint where you have the privilege also to manipulate the data, not only to select the data. So it requires distinct rights and access rights to do these kind of manipulations. Okay, so this is simply for specifying exactly data you want to insert or to delete. Sometimes also it's interesting for you to bulk upload, let's say, an entire huge RDF file into a graph in a SPARQL endpoint, or you want to delete the entire content of a graph. And for this, SPARQL provides some additional commands that are available in the SPARQL data management language. So you see here, for example, for uploading RDF data from a file, you have the load command. And here you see again in square braces a silent command which simply says, yeah, there should be a verbose output or no verbose output of the result of that statement. And then after the load, usually you specify the URI of the RDF data you want to load, and then you can specify the graph in which the data or the triples from the RDF file should be loaded into. So similar works the delete statement. So if you want to delete the content, it means all the RDF data within a graph, you simply say clear, and then you specify the graph you want to delete the data from. In the other way around, you also can create a graph with the command create, and you can drop a graph. So this means not only to delete the content, but also to drop the entire graph with the command drop, and then graph and the graph name. And moreover, you also have the possibility to copy graphs, to move data from one, or move graphs from one graph to another graph, and to add graphs to another graph. So this is also possible with the means of SPARQL. And this, as I said before, makes SPARQL a fully fledged data management language. So you might try this out with an own implementation on your own SPARQL endpoint. So for example, if you try to upload an entire RDF file into your own triple store, and then you can do accordingly these manipulations. Okay, so this was an addendum to the possibilities you have with SPARQL. So what is missing after all these SPARQL parts of the lecture we have already talked about is now, how does SPARQL really work? So SPARQL, of course, is kind of a language. It means this language has to be translated into some kind of commands which carry out these commands in the end on the SPARQL endpoint, on the database that is below the RDF data. And for this reason, there has been defined a so-called SPARQL algebra. It means there is an algebraic approach which specifies the semantics of the SPARQL language. So why is this semantics necessary or important? Of course, if you want to carry out the same operation on the same data on different implementations of SPARQL endpoints, of course you want to achieve the same result. And simply for that reason, there we must have a formal specification of what should happen when a SPARQL command is executed. And for this, there is the SPARQL algebra. It's the same like there is an algebraic model for the relational databases, for example, the relational model. You have for sure heard of that if you already have heard about databases. So here now is the algebra for SPARQL. So what do we need if we try to do or to create an algebraic approach to model SPARQL functionality? So first of all, the SPARQL algebra is an algebra-based approach to define the semantics of SPARQL, which means it defines the correct behavior for evaluation of graph patterns and solution modifiers. So this is according to the SPARQL specification. And in the end of this lecture, I give you also the link to the explicit SPARQL specification, where you can look up in depth all the things we have covered here in this small section of the lecture, and where you can deepen and broaden your knowledge accordingly. Okay, so it's about the correct behavior of the evaluation of these graph patterns. So how does it work? Usually it's a series of 3 steps. So first of all, we have to parse the SPARQL query into a so-called abstract syntax tree. So this is nothing else than, for example, parsing a programming language within a compiler or something like that. And then you create an abstract syntax tree which will further on be processed. So in this abstract syntax tree, usually you convert all the syntax parts that you find into a so-called abstract SPARQL query, into an algebraic expression. So we will see how this is achieved. And then in the end, with this algebraic expression, you can evaluate the SPARQL query, which is then a so-called abstract SPARQL query, on a given RDF dataset. So this usually is the way how the evaluation works. So 3 parts: parsing, converting, evaluation. Okay, so first let's have a look at this abstract syntax tree. So how does this usually work? So usually during parsing of a query, a parse tree is constructed. So how does this work? The parse tree usually contains objects that correspond to things that are met in the grammar definition of the language. So, and for the transformation then, we traverse simply the parse tree recursively and build the algebraic objects from the things we have found in the abstract syntax tree. So the main part, or the most interesting part within the query of our SPARQL expression, is usually the graph patterns in the where clause. So here I have the fraction of the grammar that is used here to define what happens here in the where clause. Usually you have a so-called group graph pattern, which usually consists either of a triple block, which is followed by a graph pattern not triples block, or a filter expression, or again then a filter block. And this graph pattern not triples can be then an optional graph pattern block, or a group or union graph pattern, or a graph pattern. And an optional graph pattern, sure, we know that it's a graph pattern which is introduced by an optional command, and a graph pattern, it's a pattern which usually specifies a specific graph, the named graph in that sense. And a group or union pattern then usually is started with a union, you see here. And in the end, of course, you can also perform so-called filter operations, and therefore you look at the filter constraints. So these are the important parts within our syntax that we have to respect when the SPARQL query is transformed into an abstract syntax tree according to the grammar, or the part of the grammar we see here, which helps us to translate what occurs in the where clause, in the where graph pattern. Okay, so let's continue. Usually what we do then is we try to transform what we find there. So each operation returns a result of the subquery it describes here usually. First you have the so-called graph pattern operators, which are usually then defining the graph patterns within the where clause. So we have the basic graph patterns, which are nothing else but simple triple patterns combined each other conjunctively. Then we have an operation, an abstract SPARQL operation, which is called join, which is used for a conjunctive join of two triple patterns. Then we have the left join, which usually is used for optional conditions within graph patterns. Then we have the filter operation, we have the union operation, and we have the graph operation for named graphs. So these are the basic abstract commands that we have to look at. And then there are so-called solution sequence modifiers. So first, of course, the graph pattern is evaluated, and then if the graph pattern is evaluated, then usually the results that you have in your solution, they are modified according to the given solution sequence modifier. So first you have order by, which can change the order of the results. You have the possibility according to which output variables you have specified in your select clause, you can perform a so-called projection of the triples that are returned in the result of the graph patterns operation. So for example, you are only interested in specific variable bindings. So therefore you do a projection and project only the variables you are interested in. Another thing is you can get rid of redundant information with a distinct identifier. The same is with a reduced identifier. We haven't talked about reduced, but this is somehow a weakened version of distinct. And then with a slice operation, you can define a limit or an offset. And then you also have the possibility to list, to construct sequences from multisets. So you might wonder, what is a multiset and what does it have to do here with the solution of a SPARQL query? So as you might know, of course, SPARQL queries might contain duplicate results. So therefore, the result of a SPARQL query cannot necessarily be represented as a traditional set, because in a set, each member is unique. And therefore, there can't be any redundancy. So therefore, usually in these kind of algebras, a more generalized concept of sets is used. And these are the so-called multisets. In multisets, each member can occur several times. Therefore, usually in a multiset, you denote not only the member of the set that occurs, but also the number or the frequency, how often this member occurs within the multiset. So multiset, simply keep in mind, is a generalization of the traditional sets that we are using. And the special thing about these multisets here is simply it can contain an individual more than once. So you have also to keep in mind the frequency, how often this individual occurs in the multiset. And this, of course, is important if we consider solutions for a query language like SPARQL. Okay, so these are the basic prerequisites for us. So let's now try to convert an abstract syntax tree to an abstract query. So first we have to define what is an abstract SPARQL query expression. So this usually is a tuple consisting of three major elements. So first of all, we have a SPARQL algebra expression, E. Then this SPARQL algebra expression is defined or should be evaluated on a given RDF dataset, which is here denoted as DS. And the RDF dataset consists usually of a default graph and then of a specific number of named graphs, which are given as the named graph and of course a URI of that graph. So this is the set or the set that represents the RDF datasets on which the SPARQL query is executed. And then, of course, the query has a specific form, which is given here in R, which could be a select query, an asked query, a construct query, or a describe query for a SPARQL select syntax. Okay, so the general way to convert an abstract syntax tree to an algebraic expression works always in the same way. So first step, we have to expand all possible abbreviations that you know, for example, from Turtle, for URIs and for triple patterns, into an explicit triple representation. So this is the first and most basic step. After that, we have to recursively translate the query pattern into an abstract SPARQL query pattern. And then, in the end, we have to translate also the solution modifiers. And after that, we have an abstract SPARQL algebra expression. So let's start with the first step. You see here an example of triple patterns like they might occur in the where clause here. So you have here author is of type writer, and then this ends with a semicolon, and then the author has the label author name. So we easily expand that. Usually we need for that usually the prefix definitions. So usually then we substitute all relative URIs with the help of the prefixes we find and with the help of the base directives and all the stuff that might be somewhere available. And of course, we also make full-fledged triples out of the abbreviations that are possible with Turtle. So here then in the end, you end up with 2 complete triples, which then are ended with a period. And there, of course, the properties, as you see here, contain the entire URIs of the given constants within that triple pattern. And only the variables remain the same way as they are. So we have in the lower part here, in the lower box, you see here we have the author and we have the author name as variables. So this is the first step. So this is pretty simple. So for the next step, for the recursive translation, let's take a more sophisticated example that we want to translate. So I have here an example which contains almost everything we have to translate. So in the emphasized part here of that gray box, you see the where pattern. So it means the graph patterns that have to be translated first. So I have a select query here which selects 3 variables, author, author name, and work. So this in the end should be then projections of the results that is evaluated in the where clause. And in the where clause you have several triple patterns, graph patterns, basic graph patterns that are combined here. So first we will find an author, which it means the variable author should be of type writer. And then we have the author also should have a label, which is the author name. And then we say, okay, we want to restrict all the labels only to labels in English language. So we have a filter expression. And then together to the author, URI of the author, and the name, which is a string of the author, we want, if it exists, also complement optionally the most notable works of the author, which are available here in the triple pattern author, then DBpedia, notable work, and work. And this then in the end should be combined via union, so as an alternative, combined with a triple that is the other way around, that first states in the variable which is called work, and then says the work should be authored by an author. So also we look vice versa at all possible works on novels or books, and then we look whether they have an author. And if they have an author, which is here with the DBpedia ontology property author denoted, then we also want to state the author. And this then is combined with the first part of the query via the keyword union. So this is a rather complex query. We have almost all possible query commands in there. The only thing what's missing, of course, are then the sequence solution modifiers, like, for example, the order by, the group by, which we will not talk extensively or in detail. So you can look the solution or the interpretation of the solution modifiers up in the SPARQL specification later on. But now let's focus on that query and let's further translate it. So we start recursively by identifying first all the triple patterns that we find with basic graph patterns. So we have here several triple patterns. If we start here from the beginning, we have the first 2 triple patterns which specify that an author should be a writer, and we say that the author should have a name. So this is the first one. And then we find the next one after the optional statement, which states that the author has some notable work, which is a work. And the third basic graph pattern we will find in the union part or after the union part. So here we also see that work has an author, which is an author. This is the next basic graph pattern. So we substitute simply this expression or these triple patterns that we find here with the expression you see here. We say it's BGP, and then in braces we write the triple patterns that we find here. Okay, that's the first thing. Identify or replace triple pattern with the operator P BGP. The next part then would be the identification of left joins. Left joins are, we remember that, the optional identifier. So introduce left joins for all optional parts of the query. So we see, let's go one back. So we had here the expression optional between the first two basic graph patterns. So we combine both of them within a left join. So this is then the next slide that you see here. So we have a left join over the both basic graph patterns here, which are then combined again in braces. And of course, we replace the optional keyword here and then only end up with a left join over two basic graph patterns. So the next thing then would be substitute the keyword union here with a union expression. And then, of course, we have the union of the first part and the second part. So the first part was this left join, and the last part was this last graph pattern where we have work and then author, which has an author who is an author. And this should be combined then in a union statement. And the last thing that is missing here is the filter expression. So then we execute in the end over the overall result the filter expression and then filter again in the following way that we say, okay, we apply a filter with the following condition on all subsequent abstract SPARQL query expressions, as you see here. So I translate a group with filters with the filter operator, which might be, as in our case, also only a single filter. So if you want to try this out for various SPARQL queries, you can do that. So here is the address of a query validator. So if you go to that query validator and present an arbitrary SPARQL query like we did it in our examples, then you can translate this SPARQL query directly to the abstract SPARQL query syntax, like we have seen here. So this is the first part and the simple part, the translation of the syntax tree that we have achieved via parsing the original SPARQL query to an abstract SPARQL query. The more difficult part then is the evaluation of these abstract SPARQL query expressions, and this then will be the next part here. So we now are looking at the evaluation of SPARQL algebraic expressions. So first of all, we have to look at the semantics of all these operators we have introduced. And usually, okay, here the semantics is first given in an informal way. It means here the basic graph pattern does nothing else than matching or evaluating a specific pattern on a set given of RDF triples. So the join expression usually does a conjunctive join on two solutions that I already have, M1 and M2. The union does nothing else than a set-based union of solutions that I have, and the left join can be also complemented via a filter constraint, and then I do a left join of two solutions that I have with a given filter constraint. And of course then a filter, it applies a filter constraint F on a given solution M. And then there is also something which is called an empty pattern. You need this empty pattern usually if you do a join on one and the same triple, so then you use it for denoting the identity within a join. Okay, so now evaluating a SPARQL graph pattern results in a solution sequence. We already know that. And this solution sequence, which contains all the possible mappings or matchings and variable bindings in the active graph, is what we try now really to achieve in our evaluation. So it is possible, or it is necessary, that we try to find out what are the variable bindings, the mappings of the variables which are specified in these abstract SPARQL query expressions. And when I apply this on the RDF dataset, of course, there will be bindings of these variables. They will be generated. And this is, in the end, the result. So I'm looking at all these bindings, which are here further on referred to as so-called mappings or matchings. So, and the SPARQL algebraic operators, they operate on a multiset or on sequences of these solution mappings. And this multiset here further on will be noted as a big omega. Okay, so now it's getting a little bit more formal. Besides here the informal definition of how these operators work, we will now come to a more formal definition and first start here with the basic graph pattern matching. And therefore we have to define a few formal things first. So first we define what is a so-called solution mapping. So you remember solution mapping, it's here referred to as mu. This is of course a mapping of a variable to a binding. So this is a binding of a variable to an RDF expression. So therefore this mu is also a so-called partial function which maps the variables to the number or the available triple expressions or the available RDF expressions. So then we define a pattern instance matching P. This is then the combination of an RDF instance mapping, so which is a subgraph usually, of our given graph. So it's a matching that we try to achieve. So it's the matched subgraph we have here. It's called RDF instance mapping. This is further on referred to here as sigma. And a solution mapping mu. So it means a pattern instance matching P of X is nothing else than an RDF instance mapping sigma of X and a solution mapping. So it means first we try to map all the triple patterns on our subgraph, and then we try to extract what are the variables we have here, so and what are the bindings of the variables, the mappings of the variables. So therefore it's expressed in the way you see here. And then we can define, so first we have BGP, which is a graphic which should be a basic graph pattern, and we have an RDF graph G. Then mu is a solution for BGP from G, from the graph G, when there is a pattern instance mapping in that case P, such that first P of BGP is a subgraph of G, so the pattern of the basic graph pattern that I have here, I map this, and this is a subgraph of the entire graph G that I'm looking at. And on the other hand, mu is the restriction of P to the variables, to the query variables in BGP. So it's quite simple. It's only a little bit complicated expressed. So what you see here is nothing else than, of course, we try to define what is this variable binding and how do I, what happens if I apply usually a basic graph pattern on a given graph, and then I want to extract the variable bindings, which I here further refer to as mappings. So this is the basic graph pattern matching. Okay, and then the evaluation of this basic graph pattern P over a graph G results in a multiset of solution mappings, mu, where each mu is a solution for the BGP P, for the basic graph pattern P. So you can have, of course, several mappings for the same graph pattern. Of course, it's possible. So, but it's a multiset. So therefore, we also have to take into account that, of course, a mapping can occur more often. So we have to denote somehow what's the cardinality of each solution mapping mu. And this usually is referred to as it's the cardinality over a multiset omega and a given solution mapping mu. So we define it the following way. Let BGP be a basic graph pattern and let G be an RDF graph. Then the cardinality of each solution mapping mu in the multiset omega is the number of distinct RDF instance mappings sigma, such that first, of course, this basic pattern, this instance pattern matching is exactly a pattern instance mapping, and P of BGP is a subgraph of G. Okay, but this is only the formal definition of how I, in the end, define what is the cardinality of a mapping. So just keep in mind this cardinality means this is the number how often one of these bindings or solutions occurs in the solution set. So now we have to take care about all the operators that might occur. And therefore here are the formal definitions of how the operators really work. So First we look at the union, which is somehow, you know that, an alternative. So we have two multisets, omega 1 and omega 2. And then the union of both, again, results in a mapping where mu, in a mapping mu, where mu is in omega 1 or mu is in omega 2. And it's quite easy. So the cardinality of both in the end is the cardinality of a mapping which occurs in omega 1 plus the cardinality of this mapping if it also occurs in omega 2. So it's quite simple to see that. And it works in the way like we know it. So for example, if we had as omega sub 1 here the first table where we have twice the author Jules Verne, first with the work From the Earth to the Moon and then in 80 Days Around the World. And then in omega sub 2 we have the table with, it's the other way around. So first we have work and then author, and we have the title of the work is Fiesta, and the author is Ernest Hemingway, and the title of the second one is Animal Farm, and the author is George Orwell. And if I try to compute the union of both of them, so you see I have here identical variables which can easily be combined then here, and then I simply build the union of both. So you see here the result of union of omega 1 and omega 2 according to the definition we have here. Okay, union was quite simple. Now let's continue with the filter expression. So usually a filter expression is applied on an expression E, which has to be evaluated on a solution mapping mu and of course the multiset omega. And it results in a mapping, solution mapping mu, where mu is in omega, and of course E, the expression applied on mu, evaluates to true. Okay, we all know that, of course, if I filter a result according to a given constraint, only triples which fulfill the constraint will be in the result set. This is quite clear. And usually the cardinality of a single variable mapping stays the same. Okay, so let's look at the basic example. Here we have, again, a table which consists of a column author and author name, and we have the author Jules Verne, and we have several author names in, as you see here, several languages, and then we want to filter out only the author name in the English language, and the result, of course, will be only the one assignment where the filter constraint really holds, and this is the first one where the filter constraint author name equals, or the language of author name equals en really computes to true. So only the first one will be then in the given result. And of course, the first mapping 1 will stay 1 according to the cardinality which is given. So this is the evaluation of a filter, also not too complicated. If we look at the join expression, if we want to combine conjunctively two result sets, this is a little bit more difficult. So usually what we do, or what we have to do here, is we have to merge two mappings. So usually we have a result set omega 1 and we have a result set omega 2. And the join of both is the merge of both mappings that we have here. A mapping mu1 which comes from omega 1 and a mapping mu2 which comes from omega 2. But they are only merged or mapped if they are what is called here compatible. So therefore we have to define what compatibility means. So two solution mappings, mu1 and mu2, are only then compatible if it holds for every variable in the domain of both of mu1 and mu2 that they really compute the same value. So this means if I have two result sets, I only look at the variables which occur in both of them, so at the intersection of both variable subsets. And then I only combine those which have in these variables exactly the same value, like a join usually works. So this is what the definition of compatibility here says. So now we know what compatibility means, and then we can continue with our definition. Then we say, let mu sub 1 and mu sub b be compatible solution mappings. And then the merge of these two mappings is nothing else than the union, the set-based union of these two mappings. So we can have a look at a small example here. It's here below in gray given. In this example, you see two mappings. Mappings are bindings. It means that variables that here start, you know that, with a question mark, they are mapped to a URI or mapped to a literal. So in the first mapping here, we have the variable x, which is mapped to a URI a, and we have a second variable y, which is mapped to a literal ABC. Then we have a second solution mapping, mu sub 2. There, variable x is also mapped to the URI a, and variable z is mapped to the URI b. Okay, so now let's compute the merge of both. For them, I have to look for compatible solution mappings, and the only compatible solution mappings are, of course, I have to look at the variables which occur in both of the mappings. This is only the variable x. And then I have to look whether the mappings are exactly the same. So x in the first is mapped to a, x in the second is mapped to a. So this holds. So this means this will be part of our solution. The mappings are compatible here. So in the end, what happens here is I do a merge of the two mappings, which are here compatible. So I simply map or build the union of mu sub 1 and mu sub 2. And this then results in the merge of mu sub 1 and mu sub 2. And this is nothing else than variable x is mapped to a. And then I take the rest of the mapping 1, which is variable y is mapped to ABC. And then I take the rest of mapping 2, variable z is mapped to b. So this is nothing else than the union of both. And here I have performed accordingly a join operation, a conjunctive join. So you see also the join operation is not too complicated. Let's try it now with the real definition. So here again you see join of two multisets omega sub 1 and omega sub 2 results into the merge of two mappings mu sub 1 and mu sub 2, where mu sub 1 is a mapping in omega sub 1 and mu sub 2 is a mapping in omega sub 2, and both of the mappings are compatible. It's a little bit more complicated now to compute really the cardinality of the resulting mapping, simply because there, of course, you have to look, or you have to try to combine. You have two result sets. You have omega 1 and omega 2, and you look at compatible mappings in both of them. And of course, for each mapping, which is in the first one, you have to look at all matching mappings in the second one. Then you look at the second one in the first, and you look at all matching mappings there. And in the end, you see what you get there as cardinality in the result. You get the sum over the product of each combinations of the mappings. But this is usually performed in that way for a join operation. You might already know this from relational algebra. Okay, in the example we have here, so cardinality is pretty simple because only one is here combined with one other. So you see this here. We have first table which contains only author Jules Verne and two of his works, From the Earth to the Moon and In 80 Days Around the World. And the second one contains three columns which are author, work, and release date. So we have here author Jules Verne and Ernest Hemingway. We have work From the Earth to the Moon and The Sun Also Rises, and we have the according release dates. So if we now try to do a join on both of them, of course, we have first to look at all the variables which occur in both of the tables. This is author and work. And then we have to look at the solution which are really compatible. So we have to look for which are the bindings similar. So we have here Jules Verne and From the Earth to the Moon, and in the other table we also have Jules Verne From the Earth to the Moon. These are the only ones which are in the end compatible. So they are combined, so they are also then in the result, and the result then is the combination, so the merge of the two mappings of this single mapping in the first line we see here, and this is then Jules Verne From the Earth to the Moon and the release date 1865. So that's the evaluation of a join operation. Okay, now it's a little bit, or it's becoming a little bit more difficult. because before we can evaluate the left join, we need a substitute construct, which is here called the difference, or diff. So we need this then, you will see that, for defining what is the left join. And difference work, like you know from set theory, like a difference works. So usually here you are given two result sets, omega sub 1 and omega sub 2. And this in addition can also be combined with a filter expression you see here with E. And then, of course, the difference of omega 1 and omega 2 combined, or according to the constraint you are given here, is a mapping mu. So such that mu is definitely in omega 1, such that for all mu prime in omega 2, either mu or mu prime are not compatible. So, or if you try to merge mu and mu prime constraint to the filter expression or constraint you have here evaluates to false. So which means simply you want to subtract the second part or the second solution from the first solution and combine this again with a possible constraint that can be expressed here. So and the cardinality of the difference of the two, of course, remains the cardinality, or is the same as the cardinality of a mapping from the first set, where I do a subtraction. So because things that I subtract are not again or are not anymore in my result set, so everything which is in the result set, then there the cardinality really corresponds to the cardinality that was originally there in the first set. So let's have a look at the example here. So what do we have here? We have two tables, omega 1 and omega 2. Again, we have authors and works, and we have author, work, and release date. So it's the same example or the same tables like in the example before. And now we want to compute the difference of both of them. So we want to subtract, in quotes, the second one from the first one under the constraint that we say the work equals from the Earth to the Moon. So this should also be then subtracted. So what we do here is we try to identify from the Earth to the Moon. This definitely will be extracted from the first table. And here we see also the second one, or the second mapping in the second table, Ernest Hemingway and the Sun Also Rises, does not occur in the first table. So this definitely stays or does not affect the solution of the first table, but only the first one from the Earth to the Moon here affects the solution insofar that this, of course, is subtracted from the first table or from the first mapping we have here. So the difference of the two tables in the end is the table that results here, that only has Jules Verne and the work in 80 Days Around the World as the result set. So this is the difference of two multisets combined with a constraint that might be given here. So where is it applied? It's applied then in a so-called left join expression. Just try to remember left join. In the left join, we want to express an optional condition. So it means, for example, we want to have also displayed in the answer of a SPARQL query the notable work of an author only if this notable work really exists. If it does not exist, doesn't matter. Nevertheless, the mapping will be in the solution, but of course then the optional part will be left out, and there is no mapping for the optional part, only for the first part. So this then is the result of the left join. So let's have a look here. So in the left join, again, we have two result sets on which we apply the left join. So we have omega sub 1 and omega sub 2, and we have a filter constraint here. And the result of the left join is the filter evaluation of the constraint E and the join of the both result sets, omega 1 and omega 2, combined in the sense of a set-based union with the difference of omega 1 and omega 2 with the given constraint. So we will see this then on detail that this really works. And then, of course, the cardinality of the left join in the end is the cardinality of the expression u here, which comes from the first of the join plus the cardinality of which is in the difference. Okay, so left join of the two tables of the two intermediate result sets we see here. It's the same example like last time. Again, author and work in the first table and author, work, and release date in the second table. So left join means we want to combine them, these two tables, in the sense that we definitely want to have in the result the release date. And we want to have the release date for the results we have in the first table. So we want to have author and work from the first table and want to combine this with the release date for the corresponding pair which exists in the second table. To look for the corresponding pair, therefore, you need this join operation, and then to get rid of the rest which is not found, you need then in the end the difference. So what is the result in the end? It's quite clear. So the result consists definitely of table 1, so of the first result set, and this will be again complemented then with the variable that does only occur in the second table, so in the release state, but we only the result is taken for results which already are available in the first table. So here only for from the Earth to the Moon. And this is evaluated according to the definition given above. Okay, I admit it's a little bit complicated. You can try it out on more easier or other sophisticated examples. But in the end, this is the way how the evaluation of a SPARQL query really works. To make this a little bit more clear in the end, we want to do an example evaluation on a given RDF dataset that you see here, and of course the SPARQL query that we already have prepared. So let's have a look here at the RDF dataset. So first we have a few prefix definitions, and then we have facts about books. So we have From the Earth to the Moon has the author Jules Verne. We have In 80 Days Around the World has the author Jules Verne. We have The Sun Also Rises has the author Ernest Hemingway. Then we have some information about Jules Verne, which says Jules Verne is a writer, and we have several labels, one in English, one in Russian, and we say a notable work of Jules Verne is The Mysterious Island. Then we have Ernest Hemingway, who is also an author, and we have also, again, a label in English and a label in Russian, and then we have George Orwell, and for George Orwell, we only have notable work, which is Animal Farm. Okay, so let's try to evaluate the SPARQL query. So we have already translated the SPARQL query to an abstract SPARQL query, and then we begin recursively to evaluate that query. So we start with one of the inner basic graph patterns you see here in red. So we start first with the basic graph pattern author, notable work, and then the result we achieve here are only two. We have the notable work given for Jules Verne and for George Orwell. So the first multiset as result or intermediate result that we get is the first one here, consisting of these two lines from our RDF dataset. So this is quite easy. We do simple pattern matching, and then we give the variable bindings back as the first solution set. So the next one, we look at the second basic graph pattern. That's a little bit more complicated. So we have two triples in there, and we have first author has of type writer, and then we have author has a label, and this is then the author name. So we have two variables, author and author name, which constitute here the table, which we have as a result. So this is the solution set or the solution mapping. And we have first Jules Verne mapped to two author names, first the English one and then the Russian one, and then we have Ernest Hemingway, also the English one and the Russian one. So these are the first two result sets we have to work on in the evaluation of the next one. So, and the next one that we evaluate is the left join here. So we have the left join of these two tables. Let's switch back to look first at the table. Left join here means we want to have the first one, The first one is here, if we look at it, the second one, we have author and author name. And the second one then here for the left join will be author and work. So we want to add to the larger second table we have here a possible column with work. So what we have here, of course, is author and author name, and we only have notable work for Jules Verne. So for Jules Verne, then here we complement in the column work, Mysterious Island, twice for both the English author name and also for the Russian author name. So you see here we have, again, 4 mappings for the 3 variables we have here, and this is the next intermediate result. And we can continue to evaluate our SPARQL query. So next, we end up again with a basic graph pattern we have here given in red. So we are looking for works which have an author who is an author. So this is another part of the SPARQL of the RDF dataset, example dataset we had in the beginning. So we had 3 works here, From the Earth to the Moon in 80 Days Around the World, So the Sun Also Rises, and accordingly the authors will be part of the solution mapping we have here. And then with these 2 tables we have to calculate or to compute the union. So the next step is the union of both, and the union of both is quite simple, so you merge them one after the other. So first we have this one where we had the authors, the author names, and the notable work, where we only had Jules Verne and Mysterious Island as notable work. And then the second half is here in the lower part of the result table, where you have the author names and the variable work, which is mapped here to, which is the result of the author property here in the second part of the SPARQL query. So, and this then is the next intermediate result, multiset, we have here. And now the filter expression must be evaluated. So this is the last one. Filter expression simply looks where is in the author name the author or the language of the author really given in English, and therefore the Russian ones will be deleted, and only the result of the mappings is where, of course, the constraint evaluates to true, and therefore we have here Jules Verne and Ernest Hemingway. And you see here, this is then the result table of this complex SPARQL query on the given example RDF dataset. Of course, we have left out a few things. So we do not have given the explicit definition of the solution modifiers, how they are evaluated. So there is a little bit more. And if you are deeply interested into that, you can find a detailed reference on the SPARQL algebra and the SPARQL semantics in the SPARQL specification on the web, which is first given, of course, in the material for the course. And you can also simply use this link here. Okay. With this chapter, we are done with SPARQL. So if you want to do more with SPARQL, of course, you are free to do all the exercises which are available for the course. And of course, later on also in our programming examples, we will come back to SPARQL anyway. The next part, or the next extra part of the lecture, will in the end then focus on how we can use RDF directly on the web, because right now we have only talked about the semantic web and SPARQL endpoints where data is available. But on the web usually we have to do with documents, and how are now documents and the semantic data somehow combined? This will be addressed in part extra 11 in the next lecture.